Okay. Oh, it works. I hear. Good. Yes, everything works. Thank you. Что? So I can speak English so that everyone understands. First of all, you can ask me questions later because now we'll start the talk. But the short answer is I don't know. We were going to do that, but it appeared to be very hard. So instead of doing this, we provided building with Makefiles. So if you want to not use the binary, you can use Makefiles. It's the latest version, I think, because we do not build with older version. I think it should be the latest or one of the latest versions. Okay. Let's wait for 30 more seconds. Okay, hi everyone. My name is Anna, and I'm the lead of the CatBoost team, the library that I will be talking about today. I work at Yandex. Yandex is a large Russian company. It's something like Russian Google. Maybe you heard of that. It has many things. It has a search engine which is used by millions. It's more popular than Google in Russia. It has music recommendations, video recommendations, shopping like Amazon, it has taxi like Uber. So it has many, many things in there. So it's a large Russian company. And most of our products are using machine learning. In particular, gradient boosting. And we have open sourced our gradient boosting library in last summer. So a few weeks ago, we have had a birthday of 1 year. And it is called CatBoost. It is an open source. Many people are using that. Again, a few weeks ago, we had our 3,000 of stars on GitHub, which makes me really happy. And you all can use it also. So what is gradient boosting? Gradient boosting is a type of machine learning algorithm that works well for heterogeneous data. There is homogeneous data, like or raw data like images, sounds, or text. And for those kinds of data, you need to use neural networks. They give the best result. And there is this structured data. For example, for predicting credit scoring, there will be an age of the person, salary, credit history, all of that. And for this type of data, usually the best result is gradient boosting. And you can see that, for example, in machine learning competitions, for this type of data, winning solutions are usually based on gradient boosting. The next thing is that it is super easy to use. You have your data, you give it to the model, you say model fit, and it works. As opposed to neural networks, where to have a good result, you really need to be an expert to build a good architecture. And it also works very well for, even if you have small amount of data, you still get a good model. Again, as opposed to neural networks. Because of this whole set of reasons, it is used in many, many applications. It can be used in finance, as I told you, for predicting if the person will pay the credit or not. It can be used for music or video recommendations to say what is the best song for you that you will like, and in many other things. In Yandex, it is used in many, many places. We use gradient boosting to build the results of search, to build the results of music. We have our maps, and we predict how much time you will drive. That is based on gradient boosting. We have weather forecast. That is based on gradient boosting, and many, many other things. So it's heavily used. Now about neural networks, I do not want to oppose neural networks to gradient boosting. They can be used together, and we are also using it together. So neural networks are really good for our raw data, and one way to use it is, together with gradient boosting, is the following. Let's say you have your raw data, like image, for image search, for example. Using neural networks, you build your neural features, then you combine those features with all other data that you know about the object, and on top of that, you train your gradient boosting model. And that's what we are doing. So I'm not opposing these two things. What is gradient boosting? How it works? It's an iterative algorithm. It is usually based on decision trees. You first build a simple model, one decision tree. Then you improve the model. You are building the next decision tree so that the error reduces. And you do this for hundreds or thousands of times so that you have a complicated ensemble. And with this ensemble, the loss is already very small, and you can find complicated relations in your data. That was all about gradient boosting, and that is a good reason to use that. The next slide is a good reason to use CatBoost. There are a few gradient boosting libraries in open source. The most widely known is XGBoost. And here is a comparison in terms of quality in binary classification. By the way, who of you does use XGBoost? Who of you knows CatBoost? Okay, it's not that many people who are using gradient boosting. And I think who does use XGBoost and does not use CatBoost? Okay, you will know about CatBoost now. So basically, here is the comparison of different gradient boosting libraries. In log-loss mode, in binary classification mode. As you can see, CatBoost beats all other algorithms on these datasets. Those are openly available datasets. And sometimes, like an Amazon dataset, the difference is huge. In other cases, it's not that big, but still, CatBoost usually wins the competition. This is the comparison with tuned parameters, so after parameter tuning. It is important to know that without parameter tuning, if you compare the algorithm, then CatBoost without any parameter tuning will win all algorithms with parameter tuning on these datasets in all cases except one, where LightGBM slightly outperforms CatBoost. So it's a really good result in quality. Now I will explain what are the differences between XGBoost or LightGBM, so other libraries, and CatBoost. The first one is the kind of trees we are building. We are building symmetric trees. That is really good for working good with default parameters. It helps with that, and it helps with prediction speed. Different libraries build different trees. LightGBM, for example, builds very deep trees node by node. XGBoost builds not deep trees level by level, but they are still not symmetric. We use symmetric trees. Trees where on each level you have the same feature and the same comparison. It's this tree here. That is the first thing. The next thing is the type of data we are working with. There is different type of data. There is numerical data like height, and it is pretty clear how to use numerical data in decision trees. You have is it greater than some number, and dependent on the answer you go right or left. It is not that clear how to work with categorical data. Categorical feature is a feature having a discrete set of different values. For example, with occupation you have engineer, designer, writer, and so on. So with this type of data, you need to work somehow. And the main thing about CatBoost is that it works really well with this type of data. Other libraries do not work with categorical features at all, like XGBoost, or do not work optimally, like GBM. So what are we doing here? With categorical features, we do several things. The first one is the most straightforward, is one-hot encoding, and you can do this during preprocessing actually, but if you do it inside the algorithm, then it will work faster. So one-hot encoding is when you, instead of one categorical feature, you have a set of binary features. Is the person an engineer? Is the person a writer? Is the person a PR? And so on. That is the simplest thing, and it works well if you have little amount of different values of categorical features. But if your categorical feature has many different values, like user ID or device ID or something like that, then it doesn't work at all. So what else are we doing? We are calculating different statistics based on category and category plus label value. It is similar to target encoding. Target encoding is when you have labels and you have your categorical feature. Instead of your categorical feature, you introduce a new numerical feature, which is just equal to average label value of all the objects with this category. So with this data set on the slide, you have 4 SDE, and they have labels 1, 1, 0, and 1, and your new feature value will be equal to average label, so it's 3 divided by 4. It is target encoding, but it doesn't work because it leads to target leakage. For example, if you have just a single object with this category, then your new feature value will be equal to label. When you will be doing prediction, you will not have such a good feature that is equal to label. So you will see overfitting. To not do that, we use random permutations of the data. So we permute our data, and then for each object, when we are calculating those averages, we are never looking on the object itself. We are only looking on the objects that are before this one in the permutation. But basically, the idea is very, very similar to target encoding. So to do that, we also are using priors. So for the first object, if you will calculate average label value before this one in the permutation, you will get nothing because there are no objects before this one. So for that, we are using prior. We are adding a prior in numerator and denominator. So it works even for the objects that are in the start of the permutation. That is also something you could do during preprocessing, but what you cannot do during preprocessing is using several permutations. If you use several permutations and this way build several numerical features, it will also lead to target leakage. What we are doing, we are training several models simultaneously. Each model is trained with a permutation, and then on each iteration of gradient boosting, we drop a coin, select one of those models, and select the tree structure using this model or this permutation. What else are we doing? We are also using feature combinations. Let's say you have two features, color and pet. And the color has values black and white, and pet has values dog and cat. Black and white, dog and cat. Your new feature that will be a combination of feature will have several values: black cat, black dog, blue dog. So that is feature combinations. And if you are using them, it works really well. But the problem is that the number of possible combinations grows exponentially if the number of categorical feature grows. So you cannot enumerate through all of them. What we are doing, we are inside the algorithm enumerating only in a greedy way. We are enumerating only through good combinations. This allows us to use combinations. That is the main ideas. That are the main ideas that we are using for categorical features. There are some more, and you can read about them in the paper. I will give you a link to that. The next thing we are doing, we are using a specific schema for gradient boosting. So usually, when you are building gradient boosting model, the leaf value is the estimate of the gradients of the objects that are in this leaf, and that is just the average gradient of all the objects in the training data set that are in this leaf. But this estimate is biased because you are estimating this gradient using the same objects that you build the model with. It is easier to understand if we are talking about the loss function, about the error. So if you are estimating the error using the same objects that you used when you were building the model, the error will be less. So it's biased. To make the estimate unbiased, we are using something called ordered boosting. And here for each object, to estimate the gradient, we are only using the objects before this one in the permutation. So basically, this helps to overcome overfitting, and this helps the model to give the better quality. So those were the main algorithmic details in CatBoost that are different from other libraries and give boosting quality. Now, I want to say about the modes in which CatBoost works. Those are classification, regression, and ranking. The first two ones are pretty straightforward. In classification modes, there is binary classification. We want to predict if the person will pay credit or not, so binary classification. There is also multi-classification, which type of clouds will be present tomorrow. And this one we are using in our weather forecast, for example. There is regression, when you want to predict the taxi drive duration, for example. And there is the ranking. And with ranking, it's less obvious how to use that. So example of ranking task is, what are top-end hotels in Trento? And to answer this, what you can do, you can try to predict a rating. In your training dataset, you had ratings. And to answer the question, you can try to predict the ratings and use regression for that. But you don't really need to predict the rating. For example, let's say in one city all hotels are really good and in another really bad. What you want to do, you want to give top end here and top end here. You don't really need to give the exact rating for that. So what you are doing, you are trying to use ranking within each group. We are using ranking heavily in Yandex because we have many tasks where we need it. And that's why we have many production modes for ranking. The first two ones are YetiRank and YetiRank pairwise. It's just ranking, where you have these groups, and in each group you have a rating, and then you train on that, and then you predict the order of the objects. The next one is the pairwise mode, and there are two modes also, pairlogit and pairlogit pairwise, and it's the one where when you are training you do not have the ratings, but you have pairs of objects. And in each pair you know which object was better. The difference between these pairs of modes is that the YetiRank and YetiRank pairwise, YetiRank is really fast, and YetiRank pairwise is slower, but usually it gives better results. So it's the trade-off, what you want. You want the speed or you want the best possible quality. We also have few other modes that are more specific. There is one that is a mix between classification and regression and ranking. Another is a mix between ranking and regression. And one specific mode, if you want to predict ranking, but what you care about is you want to select top one object that is the best. So you only care about the first top object. And for that we have query softmax. So I'm pretty sure that in CatBoost ranking modes are much better than in other libraries because we use them a lot in production. And we work on them a lot also. We just published a tutorial on GitHub how to use the ranking modes. So if you are interested in that, take a look, try those modes. We are explaining which metrics you can look on, which modes you can use in which cases, and so on. So now what you care about usually when you are using gradient boosting are several things. One is the quality, and I told you about that, and another is the speed. So we care about CPU speed in training. We also care about GPU speed, if you have the GPUs, and we sometimes care about prediction speed. For example, we do care about prediction speed because we have millions of queries per second, and we really need to answer very fast. But in many cases, it's not that important, but still. So 3 things we care about. First, I'll show you the comparison between different libraries. The CPU speed. We first went 1 year ago when we just open sourced, we were not that fast on CPU. And some people say well, the library is too slow. Now it's not true at all. So if you have a data set where you have many features, like the Epsilon data set in the middle, then XGBoost will be about 10 times slower than CatBoost. If you have little amount of features, then the fastest one will be LightGBM. XGBoost will be slower, and CatBoost will be a bit slower than XGBoost. So it will depend on the data set size. For large data sets, CatBoost will be the fastest. For a small data set, CatBoost will be the slowest, but it will not be 10 times difference, it will be some difference. So it will be 3 times slower than LightGBM, and more or less the same that XGBoost. It's about CPU speed. So it's seconds, 3 data sets, and 3 libraries. In the same graph I can show you about GPU, and with GPU, it is a bit different. With GPU, we are always faster than all other libraries, and by a lot. So that is the comparison that we did yesterday. XGBoost published a new version of their GPU benchmarks, or of their GPU training, and they updated their benchmarks, and they are now better. So before, in previous comparison, XGBoost was the slowest by far. And here, XGBoost is the slowest by far in case if you have many features. Again, the Epsilon dataset has 2,000 features. So if you have a dataset with many features, then XGBoost will be 20 times slower than CatBoost, and it will be, well, LightGBM will be also very slow, but not that as slow as XGBoost. And for datasets with less features, the fastest one will be CatBoost. It's 10 times faster than XGBoost, I think. In Higgs it's 3 times, in cover type is 10 times, and the next one is LightGBM. So in GPU training, we are by far the fastest ones. Now, I encourage you to use GPUs for training gradient boosting. If you are training gradient boosting, try GPUs. We are doing most of our production trainings on that. The larger is the dataset, the more is the speed up. And on newest populations of GPUs, you will get the speed up to 40-50 times, which is a lot. So you can use that. Even on older GPUs, you have, even on K40, you have 4 times speed up. But that is true only about CatBoost, not about other libraries. Now, about prediction time. We are 30 to 60 times faster during prediction than other libraries, which is also a good thing. Now, we have a bunch of things to analyze the model. We have feature importances. We have feature interaction, how well do feature interact with each other inside the model. We have per object feature importance. So for this particular object, which feature was the most important one? And that is CHAP values. Today, later to the evening, there will be a talk about CHAP values, and you will learn more about that. But here that is the example of explanation for a single object. So you can see for each feature, was it the positive influence to prediction or not, and how big was the influence. What I can say about CHAP values is that in other libraries, it is slow, especially in LightGBM, it is really slow. And in CatBoost, because we are using this type of symmetric trees, it can be calculated much faster. So you do not have this problem that it works infinitely slow. There is also a possibility for this particular document or group of documents to understand which objects from the training data set are responsible for the loss on this object or group of objects. And also, if you want to try a new feature and understand if it was good or not, we have ways to understand this, to say this new feature is good, and to say how much good, and calculate statistical significance for that. We have tutorials for all this functionality, so take a look on our GitHub. And I also want to show you some visualizations. So what we are providing is, during the training, you sometimes want to look on the values of different loss functions. What we are providing, if you are experimenting with Python and with Jupyter Notebook, you can look on the graphs of all the errors that you want during the training, see when the overfitting had started, what are the values of the metric, and so on. If you are experimenting with something else, with R or with command line utility, you can use CatBoost Viewer, which is a separate thing that you can open in the browser and see the same graphs. Or you can use TensorBoard. We are also supporting TensorBoard. So the next thing we have missing value support. We of course have cross-validation, and for cross-validation we have the same visualization. So during the training you can see how changes the average loss function and what is the standard deviation. And we also provide stage predict and metric evaluation functionality. We have many tutorials on each of those things. Not many, but we have tutorials on each of those things, so you can try them. The tutorials also have stage predict and metric evaluation that are very useful if you start to experiment. Now here are 3 papers. Here are 3 links I want to link you to. The first one is a very technical paper. It's our paper on NIPS workshop for machine learning system 2017. And you can find the explanation of how the algorithm works, like the details, how we deal with categorical features, how we do the ordered boosting. I think we have ordered boosting there also, yeah. So it explains the implementation details. The next one is more theoretical, and it explains why this scheme of ordered boosting works, why there is no bias, all of that, why it works good. And the last one is the link to our tutorials, or the link to our GitHub, not tutorials, the link to our GitHub. Yeah, and on GitHub you can find the documentation and the code and many issues. And if you see the issue that is marked as help wanted and good first issue, you can go and do something for us. And yeah, I encourage you to do that. With that, I'm done. So I will welcome the questions you have any.
Just a quick one about ranking. So you have many kinds of ranking that can be predicted. You explained before. Are these available also in the other packages of gradient boosting? Because I'm not aware of that. Maybe
no, they do not have that.
Specific of.
Yes, so they only have lambda mart usually. They do not have all of that. That is because no one is. It's not that many people who are using ranking. And XGBoost, for example, it is a research project, so they probably did not that much care about ranking.
Hi, this detailed question. The learned decision trees, are they available through, for instance, the Python package? Can I somehow get the data and see the nodes?
Yes, so I'm not sure if we already checked the code in for the JSON model. It had to be checked in yesterday, but if it is still not checked in, it will be checked in today or maybe on Monday. So what you can do, you can look into the JSON model and use
perfect.
it.
Thank you.
And we will be publishing our next version on PyP somewhere in September, in the next few weeks. And the JSON model will be available there. So the code will be available today or on Monday, or maybe it is already. And the PyP version will be available only in a few weeks, like about 3 weeks or 2 weeks.
Hey, hi, thanks for the presentations. Regarding the benchmark on Higgs boson, you are a bit slower. Do you know what the reason, if it's because of the tree architecture or if it's because of numerical?
So the CPU benchmarks, you are talking about that. Yeah, so what we are doing, when we are building a tree, we are first building a tree, and then in this tree, instead of doing one gradient step, we are doing 10 or 100 gradient steps. It depends on the mode. it helps in quality. But it slows down the training, and it starts being a bottleneck if you have a little amount of features. So it is a trade-off between quality and speed, and because we are targeting more for quality than for speed, because of that we have some slowdowns. Plus, that is about LightGBM and XGBoost together, and now about LightGBM, they have two more speed-ups that we do not have yet, but we are going to implement them. Yeah.
So are there any more questions?
Do you know how long the training time is for 1 million samples and 100 features or so?
For 1 million samples, I cannot tell you out from my head, but I can tell you I'm not sure. I'm afraid to give you the wrong answer. But with 1 million objects, you will get speed up 40 to 50 times if you use GPUs, and it will be like very fast. It will be a few minutes maybe. So you should try use GPUs, and they are also freely available, like Google Colaboratory, and on Kaggle they also have free available K80. I think they have, so you can try that. Yeah.
Thank you for the presentation. Is it possible to provide the prediction intervals for regression?
We do not provide it yet, but we probably should implement something for that, because you are not the first person that asks us about this functionality.
Okay, thank you.
So are there any more questions? Then thank you very much.
Yes, if you will have questions later, you can come grab me somewhere.
Wie lange muss das Fragen stellen? Also 5 Minuten?
3 Minuten.
3 Minuten?
Das wird knapp.
Dann zeige ich halt minus 5 heißt 5 Minuten übrig, minus 2. Genau.
Okay. Okay, welcome to the part with teaching with Jupyter Hub. We actually have two talks. First, it's my talk. I will focus a little bit on Jupyter Hub and the installation. And in the second part, Gerd Ludwig Ingold will talk about NB Grader. So, all this material of this talk is available on my GitHub repository. I will post it also on Twitter later, so you can download it if you want. What I am teaching, I'm teaching several courses. I just listed the Python-related stuff here. I'm actually a professor at the University of Applied Sciences and Arts, Northwestern Switzerland. And as you see, I do a lot of Python. In the bachelor program, there are 3 semesters Python. So in the third semester, it's a little bit geo-related. And in the first 2, it's general Python. I also do other stuff like a seminar, or in the second semester we do some game programming, but it's not what I want to talk today. I want to talk about one course. It's in the master's program. It's called Geoprocessing. It's around 14 weeks, and let me show you where. I'm teaching usually our brand new campus. Has space for 4,500 people, including students, and costed 250 million euros and is available since 2 weeks ago. It's a really nice campus. I think the architect was inspired by Harry Potter, so he invented all these stairs, the Mensa and offices and so on. So let me talk about this course, Geoprocessing. I have several problems with that course. First, what it's about. It's about big data, and I really mean big data, large data sets. There are many satellite images, aerial images, and if you have such data, you quickly come to the terabyte range, or the multiple terabyte range, or even petabyte range. But at the course, we don't use petabytes of data. We limit ourselves to about 1 to 10 terabytes of data. So as you see, that's one problem. Students, they come with their laptop. And I can't ask them, okay, here is the hard disk, please install 20 terabytes of data. And the second problem is, in the first lesson, I really hate that. If everyone has to install all modules, it takes forever. So after the first 3 lessons, solving thousands of problems with admin rights, with I don't know what problems, they have a running environment. So as you can see, the only practical solution is using Jupyter Hub. Jupyter Hub is basically, who of you knows about Jupyter Hub? Also, about half, great. It's something very simple to explain. It's just Jupyter for multiple users. Yeah. So you have the web browser. There's a proxy. It's not that important. And for every user, you have your special directory. You have a login process. You can authenticate your user. And then there is something called Spawner. I explained that a little bit later. And then there is for every user a running notebook, or even a kernel or multiple kernels. So about the user login, it can be configured to support all common login mechanisms like the OAuth, GitHub, Bitbucket, and so on. Many. It's not complete the list. We have different others, the other possibilities to log in our users. I'm not going into that. The second thing, and that's a very interesting thing, is the spawners. If you have, for example, a cluster with multiple compute nodes, you can choose one, you can use Kubernetes or whatever. There are tons of supported spawners. As long as you don't use GPUs, it's very easy. And then if you use GPUs, it's a little bit more complicated, but there are tons of documentations online for that. So the installation is really quite easy. You just have to follow. It's not just a conda install Jupyter Hub. It's a little bit more. You have to configure a little bit. But you can set it up, a simple installation, within maybe 1 hour. And if you want to support GPUs, you will find tons of documentations online. But there is not just one documentation for your specific cluster, because every cluster is a little bit different, so you need to work around that. So let me show you the most important configuration if you get started. Maybe you want to create your own logo on top of the login page. So just edit the Jupyter Hub config PI file, which is in my case on Opt Anaconda 3. What I forgot to mention is you should use Linux or a Unix compatible operating systems. Don't even try to run it under Windows. Okay, you could do that with Docker, but forget about it. So Jupyter Lab has, I use Jupyter Lab, not Jupyter Notebook from this semester on. So it's quite simple. You have to use Jupyter Lab Hub, it's called, and then that's practically all. You just have to use the URL lab, and you have to enable the Jupyter Lab. These 3 lines of code enable Jupyter Lab. So how it looks like, that's the login page. So you go, it's an URL here, you type it in, and then the students, or in this case, I log also in, username, password, signing in. Or if you configure an OAuth thing, it will be different, of course. So you can, of course, support different kernels. In our case, we have a Python 3 and an R kernel there, so we can program in Python and also in R. And I also have a Markdown kernel for those people who don't have a Markdown editor on their computer. And then you see it's Jupyter Lab, so you have all the files on this side. So the course is in German, so this is an exercise, for example, from last year. So exercise 2, here is the text, and then here should be the solution, and the students can write their solution. The script, there is no script in the lecture. There's only Jupyter Notebook based. So that's the newest version. It's not yet finished. I still have 2 weeks time. And so you have a little bit text here, and you can open the Jupyter Notebooks and follow the lecture like that. So what I also did is a small script. If I have a class of, let me say, 20 students or 30 students, I have to have a way to generate users for the Jupyter Lab, so I just created a small script. I don't want to show that actually, which call gen users. Then you specify how many, and there you have a username, password. It looks like this, generated username and passwords, and you can distribute that to the class. The second thing is, I don't want to give all notebooks at once in the first lesson. I do it like 72 hours before the next lesson. I will deploy all notebooks for the next course. And so I created a script, deploy, in my case, geoproc Pi, where I can just copy all the materials to all students. So there is an option, copy a whole directory or copy a single file, and I can make a cron job and deploy that. I can even start it, I could program it now, so I deliver the things in time. That's what it looks like. It's not very important. Now let me come to the data. I was looking for a good solution. The first thing I came up was creating symbolic links for every user inside the directory, but there are some issues with Jupyter and symbolic links, and there are also some issues with certain modules that don't handle symbolic links quite well. So what I did is just put everything to a data directory and put the data there. It's actually a network drive, but a very fast one, and all the data is logged there, and they can just read multiple terabytes of data. So that's what it looks like. It's also in our new building, the data center, and one of these racks is for the Jupyter Lab. This one is the storage, 120 terabyte of data. This one is for backup. It seldom runs. And network, it's not yet 100% finished in this picture. I just installed it last week. So as the data here, we have 124 CPU cores, 112 GB of RAM, 120 terabyte of disk space, and currently only 4 GPUs. We want to extend that in near future. So how much time I have? 3 minutes. Okay, perfect. So I come slowly to end. One important thing, of course, is how do the students react on such a thing? How is the feedback? And we have a feedback mechanism. Every semester I get the feedback of the students. And in the case of the Jupyter Notebook, there is, of course, no question, how did you like the Jupyter Notebook? So the closest question here was top score. So I think the Jupyter Notebook was appreciated. And here's some text of the students. I skipped that because of time. So I come to the conclusion. Jupyter Hub is really great for teaching. It solves all my problems, basically, with the large data sets, with the installation of modules. Of course, they can, if they want, they can also install it. But usually, because they have 10 other courses, and if every course has to install software, some students really hate that, and so it's also solved. So another thing is I don't have to write installation instructions for every operating system, for every Python version anymore. That's huge work. And also GPUs can be used by the students. And yeah, the students, they like it. And as I said, in future, we want to add more GPU power and also use the Jupyter Notebooks more for research projects too. So at my last slide, a little advertisement. If you're interested in Geo and you don't know the GeoPython conference yet, next year in June 24th to 26th, there will be a GeoPython conference. It's the 4th edition. It's about Geo and Python. You can look at the homepage if you are interested. Okay, so thank you very much. And we have time for questions, I think.
Especially about sharing the data and letting the students be able to use them. So in your case, I don't understand the scenario. So they need to access many of these terabytes of data, or maybe you have large amount of files and only few of them, because maybe there could be other solutions than just letting everyone access all the storage, because maybe when they are away at home and so on, maybe it's not so easy.
Actually, that's no problem, because all they need is the connection to the Jupyter Hub. So, and that's quite fast. The processing itself, it's just on the server. So you have the full speed. They don't have the storage on their computer, so it's all on the central server. And what I didn't say is this server has a workload of about 1 gigabyte per second read and write. So no student will have that at home, I guess.
No, for sure. But yeah, then accessing from far away can interfere with the policies of the university, or I don't know what.
No, it's no problem. We have no problem with that at the moment. It's as secure as possible, and of course we had some hackers attempt. That's anywhere, but our IT is quite good in catching them and stopping them and stop all threats from outside.
Thank you.
Thank you for your talk. Question about the cluster that hosts your Jupyter Hub. How do you dimension it, and how many students could be simultaneously working on the cluster?
That's an excellent question. At the moment, we can scale up to 40 students. At the moment, the problem there is that if too many, it's the storage at the end and the network. We should increase the network access. We should add more redundant networks there, and we could scale that easily. But the main bottleneck at the moment is the network.
Are there any other
I'm just very curious. Do you have a guesstimate of the cost of your infrastructure?
The camera, please turn the camera off. No, it's difficult. So power bill, I don't know. That's not possible. It was not possible until now, but now we have a new infrastructure where we can actually see how much power we use, especially with the GPUs. I really didn't know up to now. And the cost of all components is not that expensive. It's about, let me say, 200,000 euro.
Thank you very much.
Die Hosentasche.
Das ist nicht mehr.
Dann stimmt was mit der Verbindung nicht.
Okay. Okay, good morning, everybody. This talk is basically the continuation in some sense, even though we didn't have any contact before the meeting, of Martin Christen's talk, who gave a great introduction into Jupyter Hub. I will be less technical and I will be less detailed about Jupyter Hub. Instead, I will be focusing more on NBGrader. And actually, I won't be talking that much about technical issues, but rather about conceptual issues concerning teaching. Briefly about me, I'm a theoretical physicist at the University of Augsburg. I'm teaching programming to students of physics and material science, typically like 15 students or so. But this is going to change in the next 2 years. I expect to teach courses with about 100 students. And then, of course, I have to ask myself, how can I make this in a way that it is scaling well? And that's why I was recently looking into NBGrader, which will be the main focus of this talk. I've been involved in 2 Erasmus European projects on education and computing. ICSE for School is something I've talked about in a lightning talk in Cambridge at the EuroSciPy. And this work is partially part of Jupyter@Edu. This is a project which is done under the leadership of colleagues in Poland and colleagues in Portugal and Cyprus. So what is NBGrader? Very briefly, I'm not going too much into the details of NBGrader, but we'll touch upon a few conceptual issues. Well, the docs say NBGrader is a tool that facilitates creating and grading assignments. That's the important issue. In the Jupyter Notebook, it allows instructors to easily create notebook-based assignments that include both coding exercises and written free responses. NBGrader then also provides a streamlined interface for quickly grading completed assignments. That's where the scaling issue comes in. And well, this picture unfortunately is very dark here in this projection. This is Jessica Hemrick, who is really the brain behind NBGrader. I would say she's maintaining the GitHub repository and really the driving force behind all this. So there are actually 3 aspects I want to touch upon. I briefly make a few comments about Jupyter Hub and Jupyter Notebooks. There are 2 aspects I want to make with respect to grading in the NBGrader extension. And then I'll talk a bit about using branching paths on the basis of Jupyter notebooks. So let's start with Jupyter Hub and Jupyter notebooks. When you use NBGrader, you have a beautiful interface via Jupyter Hub to the different problem sets. So students can fetch problem sets there. They can validate them, so they can make sure that they have the correct answer and get the full number of points. And they can submit their assignments. And there's a similar interface for the lecturer. This is FormGrader here, which allows to automatically grade the responses. So there are a few nice points here. This makes it easily accessible to the students. They can access the problem sets. They have a control over what they have done. There's no need to install Python on a local computer. And as was emphasized before, we have a consistent working environment for all students. But there's maybe one point one should consider. I mean, this in our situation, it's a bit different from the terabytes of data you are using. Maybe sometimes beginners should have this experience, oh, Python, that's not something which I use remotely on some computer. That's almost like when I'm much older than most of you. When I learned the programming language, there was this mysterious mainframe computer where we didn't even have access. So that was something very remote. And in a sense, I think it's not a bad idea if students have an installation on their computer and they know this is really running on my computer. It's nothing mysterious somewhere in the web. So that's maybe an issue to think about. The second point is using Jupyter notebooks is of course great. We all love the Jupyter notebook. And when Fernando Perez at the EuroSciPy, I think that was IPython 0.13 at that time, told us about the notebook, it was immediately clear that there was a lot of potential for education. So it allows to break up the solution process. You can't read this, of course, but you see that there are several cells. You can put explanations. That's all nice to guide students through the problem set. But there is a certain danger. Students might think that doing Python means you work with a notebook. Like in Mathematica, you work with a notebook. And this is actually not necessarily true. So the question is whether at some point we should acquaint students also with using, let's say, an IDE like Spyder. I've chosen Spyder here just because it's part of the Anaconda distribution, or even at some point use an editor like, I don't know, VI or so. So that's again something one should think about. Grading. How does NBGrader work on a basic level? Well, there are basically auto-graded answers. These are functions which the students have to fill with code. And then there are basically auto-grader tests. These auto-grader tests are basically unit tests working on this function here. And there's also the possibility to have manually graded answers, but that's something I'm not touching upon in this talk. So functions, as soon as you use functions like this example here, where you see that this is the lecture view, you have the solution here. This will, of course, be taken out for the student. There is a need to explain functions very early on in the course. Otherwise, students don't know what to do. On the other hand, these are not very special aspects which are needed. There's always an argument. There will always be a result returned. So there's no problem from this point of view. You can start out with a simple explanation of functions. Students get used to logically structured code, which is nice. But they don't do the structure themselves, which is a bit a problem. And also you need to explain to students what the argument should be so that they know what they should do with these arguments. So they get used to docstrings, which is nice. But again, it's not the students who are writing the docstrings. Yeah? So these are issues one might think about and maybe discuss in the course accordingly. Grading with tests. As I show here, that's a typical test to do some grading. that actually means what we are doing with the students is test-driven development, which is great. That's something very fashionable, except that the tests, again, are not developed by the students. Right? Tests allow to give feedback through error messages. You can define your own error messages, which is very useful for students. On the other hand, my experience is that students tend to rely on the tests I'm providing. So they are not as critical towards their own code as they used to be before. And one thing one should be aware of is that stupid mistakes will always be made. So you always have to test for, did the students return a return value? Has it the correct type and so on? So I always have basically two sections of tests, the sort of trivial tests and then the really functional tests to verify that the code is correct. Final point, branching paths. I often have a number of students with very different experience. So there are students who basically don't have any programming experience, and there are students who have knowledge with another programming language. So they might have some experience even with C, and you immediately recognize that in the Python code. It doesn't look Pythonic, it looks like C. But these are people who have already programming experience. And these students shouldn't be bored by simple exercises, and also students who don't have much experience should get used to the process of going from a problem, maybe not trivial problem, to the solution, to convert this into code. Now, using real science applications for science students, for some reason, is often considered as a mental burden. So they have the impression that all of a sudden they have to do two different things. That's why typical problem sets I'm using is like choosing some simple examples from the project Euler for those who know it. I mean, my hope is, of course, that students would get hooked by these problems and try to do more problems on project Euler or Julia said, Conway's Game of Life, or even calculating pi to a few thousand digits. That's something one can do in an exercise. Sorry, this was the wrong direction. So coping with heterogeneity, well, there is one possibility, and that's what I try to do. So I have a notebook which basically explains the problem and then gives the choice to solve this problem directly for the more advanced students, or there are options to go to sub-notebooks to learn about certain things. For example, in the problem set on the Julia set, one problem for students, which is not at all obvious, is how do I convert a number into a color? So you can use the possibilities offered by the Jupyter Notebook to let them play around with colors and get experience on how to convert a number into a color. Or another problem which often occurs is that it's not at all clear how you produce data points in an image. So how do you go through the data points? What does that mean? So you can have a sub-notebook where students try to solve a partial problem and then they collect their results. So in this way, you can have a much more personalized way to solve the problem. And the only drawback here is that whenever you open a sub-notebook, well, you get a new tab in your browser. So if you have too many sub-notebooks, then you'll have a whole bunch of tabs and students will have a hard time seeing where they really are. So there's no mechanism of leaving a notebook in a controlled fashion unless the student does it on purpose. So I hope I have shown you that there are quite a few interesting issues, possibilities, but also a few points one has to think about in the way one is using these tools in teaching. And I look forward to discussing this with you either now or maybe in the breaks. Thank you.
question? Does anybody have a question? Okay, short one.
Hi, thanks for the talk. About your concern on the testing, couldn't you make the students make a function that tests other function? It wouldn't be look like a normal test writing code, but they would still be forced to test their code.
I didn't quite get your point. You wanted to...
I wanted to make the students test their own code with making a function that tests the other function. Couldn't you make it with this?
In principle, yes, but then you have to teach students about testing. And that's, I mean, what I was talking about is an introductory lecture. So there I would consider testing as being too advanced. Actually, on an advanced level, the idea I'm having, and maybe I'm trying this next semester, is you could have two groups of students. One group is trying to write a function with the least code possible, and the other group is trying to write tests to prove that this is not a valid solution. So there could be some sort of competition. I'll be trying out this. Whether it works, I don't know yet. Maybe I can report at another EuroSciPy.
Thanks.
Okay. Okay, so now one question and then move on to the next.
You told us that your students don't write the proper documentation for the function, right?
Well, in this case, not because I have to give them the docs.
I had a similar problem, and there was a very easy solution for that. Essentially, I told the students at the end, in the exam, I pick arbitrary one piece of code of you, and you have to explain me what the code does.
Okay.
So, extremely well documented code.
Okay, that's an interesting point. Well, in this case, you have to put documentation, otherwise it's not well defined what I'm asking in the problem. But that's an interesting suggestion. Thank you.
Half an hour, I hope.
Okay.
So
I just tell you until 5 minutes before 12:30. I'll show you. Okay.
Okay. Thank you.
Yep.
Hello everybody, I'm Antonino Gargiola. I'm an electrical engineer, biophysicist, data scientist, and I encountered the problem of reproducibility in my academic research because when we produce an analysis for a paper, we need to be able to reproduce this analysis later on after 6 months or after 2 years, or another group needs to be able to reproduce the same results and draw the same conclusions. So the topic of today will be reproducibility in the Jupyter notebooks, and it will be about this tension between the need for reproducibility and interactivity. That I think it's the main. Okay, I'll put the power. Okay, thank you.
Just carry it.
So this is a kind of a hot topic nowadays. Recently, Joel Grus made a presentation at JupyterCon titled "I Don't Like Notebooks," and arguing that actually notebooks are counterproductive for reproducibility. And actually, it's a very fun presentation that I encourage you to watch. And apparently, many people, especially veterans in the community, agree with this point of view. I know that there are a few in this room. There are good points there, but the goal of my talk is how we work with notebooks in a way that is as reproducible as possible. Then you can argue if you prefer using notebook or not, but it's a kind of a different question. And for me, as I said, the tension is between interactivity and reproducibility, because the more your workflow is interactive, the less is reproducible. To make it reproducible, you need to automate everything, so you remove interactivity. And this is kind of orthogonal to the fact of using notebooks or not. So there have been as you imagine, a big discussion after this presentation. And one tweet that I like to report is this from Kathleen Hudon. She's a data scientist at Netflix. Netflix is a company that is moving all their internal workflow to rely exclusively on Jupyter notebooks. So there is a big company. They do a lot of heavy computation, machine learning, and production, and they decide to base their workflow on this. So they have some clues on how to use this tool in a more effective way. And I'll take this point later on in the presentation. So what I show here is not some dogmatic view of workflow, how you should work, but it's just my experience, and other people may disagree, and it's fine. I like discussion about it. So first point, when you start a new project, you should prepare an environment. Prepare an environment means first you prepare a folder structure. You have your project, and you prepare a set of folders for data, for intermediate results, for figures, and zero order fail-safe mechanism. You put this folder under backup, like with Dropbox, Google Drive, something like that. And another part of creating your environment is the actual software environment. And nowadays you can do it with tools like pipenv or with Conda environments and Toad environments, or even Docker, in case you need to install packages outside the Python ecosystem. And this allows you to have some declarative specification on your environment, because you have this text file that is a environment.yaml or Docker file that it kind of specifies your environment and allows you to move it to another machine easily. And also specify all the versions of all the packages that you use at that time point. So this is just an example of how you create a Conda environment. I don't think there is much to say, except that you give a name and then you decide a set of packages, and you can always update it later on. Folder structure, as I mentioned before, this can be an example when you start. If you can, you keep the data in your folder. Otherwise, you put links, for example. I will talk about data preparation in a second also. And also, I like to put a results folder for CSV files of processed data, and figures folder for this helps in preparing summaries, as I'll illustrate later on. Okay, so preparing your data. Most of the times, data comes from heterogeneous sources. In my previous academic research, data was coming from different instruments, but was the same type of data, but acquired by different brands of instrument or with a slightly different configurations. So they had all kind of different data formats. So I had to pre-process this data and transform it to a common format. So that from that point on, all the analysis will be independent of the source of the data. Another point to think about is how you structure your data in a way that is easy to work on. For example, here we have the comparison between tidy form and long form data frame. So you need to think about how you like to operate on this data, because it will make the code much simpler if the data is already in the right form for your analysis. The notebooks. The notebook is all about narrative. So when you start a notebook, first thing I think you should think of is building a narrative. What is your the message and the purpose of that notebook? Of course, make use of all the powerfulness of the notebook in using headings, equations, figures, links, because this is what makes a document a notebook document really a rich document that is useful for sharing your data to other people, your analysis to other people. When you document and describe your analysis, document purpose, not mechanics. This is a general concept. It's not only in the notebook. When you write doc strings, you don't want to explain the implementation details. You want to explain the purpose. You want to be not too long in the explanation. Try to be short but precise. And another little trick that is useful is printing the library's versions. This can seem kind of redundant if you already save your environment file, but it's always useful to have another layer of checks. It's always there in front of you. Maybe you forgot to save the latest version of your environment file. So this is another thing that takes no time, and it's always useful to keep in mind when you start a notebook. The other aspect on the notebook is how you write the code in your notebook. And again, the principles on how you write code in the notebook are not different, very different on how you write code in general. So these are kind of software engineering principle. So you, especially in the notebook, that is the highest layer of your analysis, you try to use a linear structure because it is a narrative. So you don't want to branch a lot inside a notebook, otherwise it's hard to follow. And for the same reason, you want to keep it simple and short if you can, in order to don't explode in complexity. So if you need different tasks, you use different notebooks. And then related to that, you keep one primary outcome. This is from a mindset, because it allows you later on to scale in complexity. Because if you have one outcome, you have one set of results, and you can standardize this set of results and then reuse it in another notebook. So you have a kind of composability. So this is a kind of general principle. And of course, always remember to do restart and run all, because there is the issue of executing notebooks interactively with the cells that are run in random orders, and then you can overwrite variables. So you have this, what is called a hidden state. And many times beginners are not aware of it. Maybe we don't do a good job at explaining this aspect. So the solution is simple. Do restart and run all and check that you get the same result. Okay, so now we'll see an example of from the cradle to the grave of a project. You start from your first notebook. You already created your project structure, your environment. And what's next? When you write your notebook, keeping in mind all the concepts that I told before, you start writing simple commands, and then you start repeating. You will find patterns. So at that point, we use the dry principle. Try to don't repeat yourself. So you use loops, but even better, you use functions. So write functions is an important abstraction to make your module, your code easier to understand and to scale. And once you write a function, it's easier to write a test for that function. And it's not that hard. We have seen it with the previous talk. That was a beautiful example. You have a function, and then you have 2-3 asserts under the function. And these are already your unit tests. And when you write it in this way, then it will be easier later on to move this to a proper Python module, .py file, and you will have also the unit test already written. Okay, so as the project matures and your notebooks become more bigger, you start to split notebooks. You want to keep in mind also to save intermediate results, because you don't want a long, big analysis and having only the final result, and if anything goes wrong, you don't know why. So save the intermediate results, for example, CSV files, if data is not too big, or HDF5 file if it's big. But if you can, text-based files are better because you can diff these files if you put it under source control. And also keeping figures of intermediate results allow you to bring these results out of the notebook or inside other notebooks, depending on if you need to build presentations or if you need to create a notebook summary that we will see later. And another important aspect is once you have your set of functions in your notebook that you kind of understood that are the core analysis or core parts of your analysis, you just copy these functions in a .py file. And then you copy the assertion in another test.py file. And this is your unit test. With PyTest, you don't need any special syntax. The assertion becomes automatically unit test. And in simple cases, you don't need to do nothing fancy to make this transition. It's really smooth. And then at that point, you can commit all your Py file. You take advantage of the powerful IDE, so with the linters, and it really helps maintaining complex functions. Because one of the things that we want to do is remove the complexity from the notebook and put it in libraries. And the notebook is a kind of outer layer that gives the overview. And for short projects, if you know that the project will not last long, you don't have huge notebooks, you can even commit the full notebook with all the figures to a Git repository. And MBDime is a really cool tool to do diffs between notebooks. And I recently updated it, and because I had a very old version, and I found that now there is a button that shows up in the notebook that allows you to see a graphical diff between your current notebook and the last committed version. So you keep track of the differences kind of easily. In the case where the project is not so big. The problem of committing the full notebooks is that with all the figures, the Git repository can explode if this is a long-running process that will go on for many weeks or months. So how do you deal with the projects that continue to grow and for which committing the full notebooks to Git is not a solution? You structure your work in a slightly different way. First, you have many notebooks that can share the same library files that you created before. These files live in the same folder as the notebooks and you import them, but they are shared from many notebooks, so you don't repeat yourself. Then, if you have multiple notebooks that are similar, instead of doing copy notebook and then you have another version that is almost identical except for 1-2 parameters, you parameterize the notebook. It's possible to run a notebook with some parameters, and I'll show you how in a second. And related to parameterization, once you have this system set up, you run your notebooks in batch. So the way to do it is you save your original notebook without outputs. So this notebook you can commit it to the Git repository because it's just a JSON file without big figures and so on. Then you save the executed notebooks in a subfolder that will be reports or output notebooks. These will be bigger files. And from one single source notebook, you can have several output notebooks depending on how your parameter changes or the data file that you choose as an input and so on. So this will give you the ability to keep track of the code under source control and have graphical reports of your different analyses. And this is an example of a project that uses this approach. As you see, you have, for example, you have a data folder with 3 experiments in HDFI format. Then you have results folder with the CSV file that are saved by the notebook. The notebooks are in the main folder together with the Python modules. So for example, here you have a loader.py with functions to load and transform the data. And then you have analysis.py with your core complicated analysis function. Then you have an analysis template that is this notebook without output. And through the index notebook or master notebook, you run the analysis in batch, changing the parameter that is the name of the file. And you obtain as an output the executed notebook in this folder. And you obtain also the CSV files in the result folder. Okay, so when the project continue to mature, so you consolidate in this workflow even more. So you parameterize all your notebooks and you take care of building a good summary notebook that will take figures that you saved in the analysis notebooks, showing CSV files, whatever you need to present at the end. So how to parameterize the notebooks? This is maybe is not very common way to use a notebook. Let's start from an example. This is from a paper that I published a few years ago. That's the summary notebook. At some point, I define the name of the notebook template, and then I have a function, run notebook template in this case. And automatically, this function runs the same notebook on 5 different data files that are called D7, D12, D17, and so forth. And the output in the notebook will be links to the source notebook, the first link that is empty, and the links to the executed notebooks. So if I want to see the result on the file 22D, I click on this, and it will open the fully executed file. And since this is a notebook, I can rerun it interactively. Then I find an issue. I can go back and modify the template notebook and rerun all the analysis in batch. Another part of this is that I can show CSV results, like I load it with a pandas data frame and just display it. So you have kind of a summary of a batch execution of parameterized notebooks. And since this is a CSV file in the results folder, you can add also a link. So you click and you download it and you can do something else. So this is a good way to present, for example, for a paper, but I think also inside a company you need to share work between groups, and this is an excellent way to do it. Okay, what tools we use? That example was just a handmade function. After I did that first experiment, I realized that was a kind of general thing to do. So I created this little MBRun file that is on GitHub that contains only one function, and then that you can take and put it in your project is nbrun.py. You vendorize it inside your project and you import the function run notebook that allows you to run notebooks with parameters. That's the stupid way to do it. The smart way to do it is use Peppermill from Netflix, because I just discovered actually a few weeks ago when there were that 2 blog posts about how Netflix use notebooks internally. I discovered this package called the Peppermill that does exactly the same thing in a much nicer, more sophisticated way. It allows to parameterize notebooks graphically if you use the interact interface to show notebooks, and has other fancy features like saving data inside the notebook. It becomes a kind of store for your data instead of saving in separate folders, and also to tag images, figures that you create, so that you can query your notebook from another notebook to retrieve the data and the figures. So it makes, in principle, easy to create these summaries I was talking about. Okay, before, so let me finish. How many minutes do we have?
A few minutes.
Okay, I want to show a really quick demo of how it works. If we have a, so this is an example of NBRun. It's not that I care so much to make advertisement for it, but it's the concept that matters. You have a master notebook here. The example notebook, you import NBRun here, and you call the template notebook. Here, I think I did a typo before. So let's see what happens. I run a loop, and I call the notebook with different parameters, just as an example. But demo effect, okay, is running. So the result is a series of links. Every time you execute this notebook, you get a link to the source notebook and a link to the executed notebook. So if you click on the executed notebook, I insert a little cell here that tells me the execution time and so on. And the way it works is really stupid. So the runner function insert a cell as a second cell in your notebook. So the first cell will be your default parameters for that notebook. The second cell are the injected parameters from the runner function that will overwrite the default one. So without complex infrastructure, I just run the notebook like that, and I have a print with, in this case, analysis A on dataset 0, because I was looping on A, B, C, and 0, 1, 2, and 3. So that's the example of how to use it, and that's the folder. To go back to the just last point of the presentation is when you create libraries out of functions, sometimes these libraries become more general than for a single project. So you want to create a Python package. Even if it's only for yourself or your team, it's always convenient to have it as a separate Python package. But then it's harder to keep track of the version. And an easy way that I found is using Versioneer. That is a project you find in a public domain on GitHub. And it makes your, the version of your library automatically computed based on tags and Git commits numbers. So for example, here, Scikit Optimize use Versioneer, and I downloaded the development version, and I get this version. That means that is version 0.5.2, 36 commits since that tag, and the exact commit is that one. And this is really useful, especially for your custom packages, because you will continue to modify it, and maybe two different projects may use different versions of your custom library. So then you will lose track of which version you used where. And this helps a lot. And these other examples, how you can print versions in the notebooks. This is another package of mine in which if you don't commit changes to your library, the other cool thing about Versioneer is that it will show dirty. So you know that you are using a version of your library that has not committed to Git yet. So this should ring a bell, and you should go commit the modification first. Okay, conclusion. As a take-home messages for this talk, what I suggest to do is curate your environment, so folder structure and actual software environment. Think about building a narrative for your notebook. So you're telling a story. You have a clear purpose. Move all the complexity, as much complexity as you can, to libraries, and automate all the execution of the pipeline. And I think with these steps, you really, if not solve the problem completely, but make a huge progress towards reproducibility. Thank you for your attention, and do notebooks reproducibly. And I'm looking for a job, actually. So.
So you have mentioned Versioneer at the end of the talk. And have you tried setup tools SCM, or have you encountered it on the web? Because I had also the same problem, that I wanted to include the GitHub SHA code into my version, so that committing to GitHub automatically gave different versions to my project, and using Versioneer, it was a little bit cumbersome to include the Versioneer PI source file into my project and commit it. And if I want to update to a new version of Versioneer, I had to download it.
You never update Versioneer. You just it works by vendorization. So you install this package that is Versioneer. It's called Versioneer, and then you run a command that you look in the documentation which one it is, and will copy a special .py file in your project that automatically will create the version. So if it works for you, there is no reason to update Versioneer ever.
Actually, with setup tools SCM, it's a regular Python package you have to import, and it does basically all the things that Versioneer does.
Yeah, I'm not aware of it, but yeah, if it's the same functionality.
Yeah, it's an alternative, just to mention.
Sure. Thank you for bringing this up.
In which extent is this automatization of the workflow based on the notebooks? This is the stupid question. Better than automating my data analysis workflow, writing analysis scripts and then running in batch those scripts, and then inspecting the intermediate results, maybe via one notebook.
How do you expect?
Why notebook and parameterized notebooks become better than scripts?
Because at the inner level, you have your analysis notebook, that is the template. And when you execute it, you save many versions of this notebook with the different parameters. So it allows you to go back and see this report with the code, figures, description, all in a consistent document instead of opening a folder of figures and trying to link where the script generated that figure and so on. On the outer layer, when you build the summary, it's more convenient because instead of having a master script that run all your analysis, you get something like that, what I shown before. So this is the master notebook of a paper that I published. And okay, it has a lot of description at the beginning, links to different figures that were generated in the paper. And after some explanation, it starts executing notebooks like this. And you can link to your executed notebooks. This is harder to do with a script. You have your script, and then you need to navigate to where the results are. So you have a nicer HTML kind of summary. And you have also links to CSV files. You see the tables right there. You see the figures right there. Because down, you see there is this figure. So this is the result of this figure is created in another notebook. And I show it here as a summary. And I have all the explanation where this figure comes from. So I think this is a much richer way to present, and it actually improves reproducibility and the ability to explain your analysis to a person that never seen before, compared to a script-based.
Hello, thank you very much for your talk. Really enjoyed that. I have one question. In the end, you did say, all complexity goes to libraries, and I agree. But in the beginning, what you show us through your example is that you wrote your code in the notebook and you test, and then you move them into a Python file. And for me, you're missing, the helpful things your editor does, like linter and things like that. So what are your thoughts on that?
So my experience is that I start writing a function in the notebook, and then when I'm barely happy with it, I move it to a text file. And the linter helps a lot. Most of the times I find issues. Maybe I'm using a global variable in that function. This is really common. You're using a global variable in the function and you don't notice inside the notebook. But the moment in which you move it to a module, the linter immediately flags it and you fix it. So, because maybe I start typing commands one after the other. It's not even a function. So if you start from zero, if you know that already you need to write a function for something, you can write it right away in the text editor.
Hi there, thanks. So I'd like to echo a bit what the person before the previous person said about the scripts organization. I mean, once you make the concession that you're going to have one output per one notebook, you're really back to a script with bells and whistles. Because, I mean, that would be the use case where people can't take a script because they want multiple figures from one notebook, which is not what you should do if you want a reproducible document. So, and how far would you say that all of the additional work which you need in order to transform a notebook into a function, which you do not need to transform a script into a function, is compensated by all of these features? I mean, I'm getting a bit the impression when you're saying that, yeah, you can look at your files in the notebook and where they're organized and how they're linked, that basically you're trying to include script execution and a bit of IDE and a bit of file manager into your notebook, sort of situation where when the notebook is your hammer, everything looks like a nail. And I'm unsure how these features really compensate for the
that is messy. So you want to always to organize and move your functions to a library. So this appliant to keep track of all these steps. For me, as I said, is your mileage can vary.
Okay, are there any more questions? If not, then thank you very much. Have the bench.